Okay, so now we're going to talk about a very important theorem, okay? So one of the central questions in the study of differential equations is whether a solution exists. So does a given differential equation have a solution that satisfies the initial condition yx naught equals y naught? Okay? Or in the language of solution curves, which we saw above, we could say, are there any solution curves that run through a given point? Okay. So one question is existence, and suppose you find one. The next question naturally is that the only one? And that question is uniqueness. So when a solution to the first order initial value problem exists, is such a solution the only solution? In other words, in the language of the curves, is there precisely one solution curve of dy dx that runs through x naught, y naught? Could we in this situation above had another curve that also runs through 0, -1 and solves the initial value problem? Okay, so that's the question of uniqueness. So very central question in the study of differential equations is the existence and uniqueness of the initial value problem. Sometimes we'll also talk about boundary value problems, where instead of specifying the point, specifying the initial point, you specify, different points on the trajectory, or it could be two separate points for say second order differential equations. That's called the boundary value problem, which we'll talk about. But for now, let's focus on the initial value problem. So explore the solutions to the initial value problem that we see here. Now we've spent some time on this differential equation to really kind of go deep into differential equations. And we see different solution curves. So we have the pink there, that's y is equal to 1 over 16 x to the fourth. Okay, that was a solution to the differential equation for sure. We actually could obtain it from the family of solutions, the one parameter family of solutions. And choosing y of 0 equals 0 would have fixed c to 0, okay, in that one parameter family. And so we would get y is equal to 1/16 x to the fourth. And it is indeed a solution to the initial value problem. Y equals 0 also solves the initial value problem. Okay, so this orange function that just on the x-axis there, that's also, it's the trivial solution, but it actually solves the initial value problem. Okay, we could even find another solution, one that follows the pink on the right hand side, and then we paste the y equals 0 solution on the left of the y-axis. Okay, and that's the blue solution there. It runs like this. And so is there a solution? Does a solution exist to the initial value problem? Absolutely. Is it unique? No. We just found 3 different solutions to the initial value problem for this differential equation with this initial condition. There are at least 3 solutions to the IVP. The solutions exist but are not unique. Okay? So naturally, we're going to ask the question then about the existence and uniqueness. When can we guarantee that? And so consider the first order initial value problem. dy dx equals fxy with the initial condition yx naught equals y naught. Let R be a rectangular region in the xy plane defined by x being between a and b and y between c and d that contains the point x naught, y naught. So that rectangle contains the initial point in its interior. So it's not at the boundary. If f, x, y, and partial f, partial y are continuous on R, then there exists some interval around x naught. We're not specifying how how big that interval is, so just that h is strictly greater than 0, contained in a B, and a unique function y of x defined on I naught, this interval, that is a solution to the initial value problem above. Key word here is unique. Okay, so we found conditions for getting for one, knowing that a solution exists, and two, knowing that it's unique. And the conditions are that fxy and partial f partial y are continuous in a rectangle. And for the purpose of this theorem, we're demoting y as if it was also an independent variable. Okay, y is actually seen as a function of x. Okay, but just for the purpose of checking continuity of f in partial y, we demote it. So this is how it looks in picture. So here's the initial value problem, right? You have a y naught, you have y of x naught equals y naught. Okay, so that's, you could translate that to this point here. And we're saying that if f of xy and the partial derivative of f of y is continuous in the orange, in the blue, the light blue, then there exists some interval, this purple here, okay, where you do have a unique solution. So this, this picture just shows you that it doesn't have to be all of the blue. It doesn't have to be all of the rectangle. You're only guaranteed some interval. How big it is, this theorem doesn't tell us, but we do know that we can find some interval, even if we have to shrink it really small, so that we do have a solution to the initial value problem. So I make some remarks. The conditions in the theorem are sufficient, but not necessary. In other words, there may exist unique solutions to the first order IVP that do not satisfy the hypotheses. We're given that if f is continuous and partial f partial y is continuous, then a unique solution exists. But that doesn't mean that if a unique solution exists, that the f has to be continuous and partial f partial y is continuous. So that's just saying that the conditions are sufficient but not necessary. Okay, we check those, we're guaranteed we could find one, but we could perhaps find one that doesn't satisfy the hypotheses. For existence of a solution of the initial value problem, but not necessarily uniqueness, it is sufficient to assume only the continuity of f of xy. Okay? So if f of xy is continuous, then being careful with intervals, you can get the existence, okay? That you know that a solution exists, but not that it's unique. So, for example, multiple points. But if you add the additional hypotheses that f sub y, which is the notation of subscripts for partial derivatives, so this is the same as that, okay? Then if that's also continuous, then we have sufficient conditions to conclude that not only does a solution exist in some interval around the point x naught, but that it's unique. And so here I also emphasize in the third remark that the theorem does not tell us the extent of the interval of existence for the unique solution. Thus, it's a local theorem. So you just have a point, the initial value point, okay? And, f is continuous, partial f partial y is continuous, then, okay, you have some guarantee about what's around that point. It's a local theorem. You can't say much about the extent of that solution, okay? You don't know anything about how big that interval is, in other words. So explore under which initial conditions the differential equation has solutions and unique solutions. Must we assume restricted intervals for unique solutions for the initial condition y of 2 equals 1? So here we have fxy is equal to x times the square root of y. It's continuous for x from minus infinity to plus infinity, and for y from 0 to infinity. Okay, y can't be negative because you're taking a square root. So f is continuous in that rectangle, okay, which is just basically the whole upper half plane, including the x-axis. Thus, solutions exist there. Okay, so we're guaranteed that solutions to the initial value problem exist there. Moreover, if we take the partial derivative of f with respect to y, we get x divided by 2 square root of y. That's continuous on the upper half plane without the x-axis, because we can't divide by 0. So notice these two intervals are not the same. Okay, we're guaranteed solutions in that rectangle, but in this restricted rectangle, we're guaranteed that the solutions are unique. So if you don't include the x-axis, you could get unique solutions. Thus, unique solutions to the initial value problems exist for y naught strictly greater than 0. Okay, so this is the with the initial condition y of 2 equals 1. It may not extend beyond 0 to infinity, as seen in previous example with two solution curves passing through 2, 1 and 0, 0. So let's take a look at that. Okay, so we're basically checking, we're using this theorem to check this problem here. Okay, and we just found that in the upper half plane, and here's the point, say 2, 1, or we'll draw it here. I actually have labels. So here, okay, notice that it seems like two curves are running through that point. It's almost as if that contradicts what we just said, that the solution is unique. The solution is unique up to a certain point. The theorem did not give us how big the interval is. So as long as we restrict ourselves to 0 to infinity, so as long as we restrict ourselves to an interval here, okay, then this solution's unique. Okay, and notice that's actually a pretty big interval. The theorem actually just tells us that there's, around some point, okay, around some interval that contains this initial point x naught, you'll get a unique solution. Here we see we could extend it from 0 to infinity, and that's what I mean over here. Okay, so I is the interval, may not extend beyond 0 infinity, as seen in the previous example with two solution curves passing 2, 1 and 0, 0. If you restrict to this, there's only one solution then, right? The solution in blue, the curve in blue and the curve in pink only are different to the left of the y-axis. So for x is strictly less than 0. Okay, so here just by inspection we were able to find the interval where we're going to get a unique solution. But in general, we don't have a way of figuring that out from the theorem. And I also make the remark here that the boundary value problem, about the boundary value, what boundary value problems are, basically instead of specifying the initial point, we could specify different points that the solution curve should satisfy to fix the in-parameter family. That's called the boundary value problem. I should also point out that this theorem that we discussed above, a specialized version of it, a kind of variant of it, is called the Picard-Lindelof theorem. Okay, it's kind of given in a different language, with something called Lifshitz continuity. Here we have a stronger condition with partial f, partial y. But at any rate, there are several variants of this theorem. And so if you want to explore more, that's what the theorem is. That's a starting point, at least. It's called the Picard-Lindelof theorem.